All right, let's get started. So today we'll talk a little bit more about game theory. Um, so there are a couple of things we'll do. It'll be fun. The first thing we'll like to do is to recap the minimax theorem. Very interesting result almost 100 years ago. And many ideas in this course will be built on this, right? Uh, so later on, in fact, maybe next lectures, there will be ideas in IL, IRL, or reinforcement learning with human feedback. We'll build on some of the formulation of these problems as a minimax game or zero-sum game and derive algorithms on it. So last time we basically present one version of minimax theorem. It's the simplest form of normal form two-player zero-sum game, like rock, paper, scissors. We'll generalize this idea today to more general action space. So potentially, each player might play some strategy in some vector space. Okay, and maybe the payoff function is not exactly like rock, paper, scissors, but there are also very clean extension of the kind of theorem we saw from last week that also holds. So one key idea from last lecture is that, well, how do we prove the minimax theorem? 100 years ago, more than 100 years ago, or roughly 100 years ago, the proof was rather complicated. But for us, the proof is actually very simple. It's a simple proof by contradiction with the existence of no-regret algorithms. So the fact that these no-regret online learning algorithms exist means that minimax theorem has to hold. Okay? Another way to say this is when you play a two-player zero-sum game, it doesn't matter who moves first, as long as both players are allowed to do randomization. Okay? So today we'll essentially talk about the same proof idea with no regret algorithm. Instead, we'll state it as an algorithm. Right? So last time we're using the existence of a no regret algorithm as a proof strategy to show that minimax theorem has to hold. Today we'll actually turn it around and use it as a way to compute minimax equilibrium, like Nash equilibrium for these sort of games. Okay? So solving approximate minimax equilibrium. If you know a little bit of game theory, for this class of game, this is sometimes just called a Nash equilibrium. You might get a misleading idea of what Nash equilibrium means from A Beautiful Mind. Have you seen that movie? I make that joke every year, but now I realize this might be a class that we're born after the movie, which makes me a little sad. Well, not sad, but like, it's a different sentiment. Yeah, so we'll go through one example. So we'll be talking about these games mostly in abstraction, but you might feel it's a little dreadful or dry, but what I want to relate to something we already talked about, which is the max entropy problem. Okay, so if you remember a few lectures ago, Drew gave you this idea of how to maximize entropy subject to some sort of moments constraint. Today we'll actually view this problem as a zero-sum game. Okay? And it's quite cool. And in particular, if you take like a intro to machine learning course, at some point you might learn something called convex programming, convex duality, Lagrangian, the KKT conditions, all that stuff. I never quite learned this stuff properly. In fact, I think about all this stuff from a game theory standpoint of view. Like my game theory or game theoretic intuition about this problem is my first instinct. So we'll talk a little bit about how to view this sort of problem as a zero-sum game, which I found to be more intuitive. Okay. At the end, if there's time, we'll talk a little bit about extensive form game. We probably don't have time to get into full-blown details of what extensive form games are. It usually takes like a few lectures to go through these ideas because it's kind of the dense topic in terms of notations. To talk about these things in detail in full technical treatment, you need to define a set of things. But with the things we already covered, I feel like we can already talk about some of the most interesting advancement in extensive form games, which is bringing some of the no-regret algorithms to solve these sort of games. And most notably, if you pay attention to some of the ideas coming out of CMU in the past decade, one idea or one sort of research agenda, mostly led by Thomas Sandholm and Norm Brown, is how to solve poker, like as a two-player zero-sum game or multiplayer games. And one of the core ideas of making these advancements is playing no-regret algorithms locally at every decision point. So with the tools you have seen so far, you can already gradually appreciate some of these development in this literature. So we'll scratch the surface on this topic today. All right. And who's scribing today? Just you? Who's your friend? Oh, that's your friend. Sorry. Cool. I mean, I trust you 100%, but sometimes good to have at least two people. Okay. So just a quick recap on the set of notations we talked about from last lecture. This is the simplest form of games we'll talk about today, and we'll move from here to more and more interesting games. But usually in game theory 101, you would talk about games of this form. You have two players. One is sometimes called row player. The other is called column player, just because the payoff matrix is usually organized in a two-dimensional matrix. So they have action sets R and C. So far, you think about them as discrete and finite. If the row player plays strategy I, and the column players play strategy J, like it will incur some amount of money exchange. So the column player will have to pay the row player some amount of money determined by this matrix. Okay? So another easier way to think about this is from now on, maybe it's useful to think about one player as the maximization player, the other as the minimization player. You know, the rows versus columns, they're somewhat arbitrary, but it's maybe more useful to think about as one of them as player who would like to maximize the payoff function, the other is just trying to minimize it. So one matrix is sufficient to describe the whole game because they have exact opposite interests. Okay. So arguably one of the most important results, or one of the most important results that lay the foundations of game theory is the minimax theorem that we spent a whole lecture last week talking about this. Mathematically, it's very simple. Let's read this again, right? So like the point of minimax theorem is the simple idea that ordering does not matter, at least in this particular type of games, right? So last lecture, where's Stephen Mann? Here. Last lecture, Stephen Mann and I were engaged in an epic battle of rock, paper, scissors. And Stephen, as a smart person sitting in the front row, naturally has the right intuition that when you play a game like rock, paper, scissors or two-player zero-sum game, you naturally want to go second because you want to see what the other player is playing. Okay. The question is whether you can actually have some arbitrage as the person going second. The minimax theorem is saying that you don't actually. All right, so it really means that if both players are allowed to randomize among their strategies, the two players, whether you go first or second, if you play the right strategy, you will get the same payoff. Okay, so the way you read this again is read it like English from left to right. So max min of this payoff means if I ask the maximization player to go first, to think about how to optimize, anticipating the second player to screw this guy up, try to at best with using the best strategy to minimize. How would this player solve this game? Okay, so this is like maximization player go first. And this is the opposite, right? You also read it from left to right. This is asking, well, if I'm asking the minimization to go first, anticipating the max player to go second. Okay, what should this player play? Okay, so both ordering will realize some payoff, like how much the max player gets paid at the end of the day. The theorem is just saying that the ordering does not matter, and it will achieve the same value. And this is sometimes called the value of the game. Okay, any question? Okay, so one thing that's important to remember, this is called the game value. I know this sort of game is often called zero-sum game. This does not mean the game value is 0. Right, so it should not be hard to convince yourself this is the case. Like, I could be playing a game where in order to enter the game, the max player have to pay $5. The minimization player don't. That doesn't change the nature of the game. It's still the same sort of strategy. But that would be like a sum equals 5 game. Right? So this is just a quick clarification. There was some question about that. Any question? Val is like a self-realizing definition in the sense that once you know minimax theorem holds, you know this equality, the first equality holds. Val is just defined as this minimax value. Good. Cool. Okay, so far everything is clean and nice, and the more pleasant surprises, this not only holds for this sort of rock, paper, scissors style games, it holds for more interesting games, right? So here's a generalization. So here, I would just think about X and Y as the strategy space, and I assume these are just continuous sets. Assume to be convex and compact. Does anyone know what compact means? A set to be compact?
Closed and bounded.
Closed and bounded. You took measure theory before. Yeah. So I actually don't know what it means. One of the instructors, not me, is not the biggest fan of measure theory, but yes, it means closed and bounded. So for example, if you look at an interval that include the two endpoints, like as in a closed interval, that will be compact. So it's not too important. There's further generalization here. And you have a utility function or the payoff function. Concave in X and convex in Y. Okay, so this means this is the payoff function. Let's call it the payoff. This means if I fix one of the variable, let's say I fix Y, and look at what the function is as a function of X, that should be a concave function in X. Okay. Vice versa, right? If I fix X and look at it as a function of Y only, it should be a function that is convex in Y. Okay. So so far, maybe this is sort of going in the direction of what you expect, but you also have the same So the minimax theorem exactly holds. This is not the most general condition for which to hold. Like, there's like further generalization that I won't talk about. Oh, this is ugly. Like, there's a thing you can look up if you can fall asleep at night. It's called Sion's minimax theorem. So if you look at the history around the 40s and 50s, in the last century, there's basically a line of work that's basically started with von Neumann's minimax theorem that look at, well, under what situations that min-max equals max-min. And I think this result was first stated by an author named Schiffman, but later on, I think Sion's minimax theorem is maybe one of the most general form. But it holds for classical games like this, right? Yeah. So, but the most interesting special case for this function is sometimes the special case we look at so far is what? So like, the special case we have so far, we basically have the strategy space. The spaces for X and Y are just the probability simplex over the rows and the columns. So probability simplexes are closed and bounded and convex. And this sort of utility function that looks like a vector times a matrix times another vector, this is called bilinear. This form function is called bilinear because it takes two input. It does have a product, so if you look at the input as a whole, if you look at X and Y as a joint input, this function is not linear because there's some product like X times Y. But if you fix one group of the variables and look at the other, they become linear, right? A lot of the stuff we talk about in this class will take this form. So, but it is just a special case, this more general minimax theorem. Any question? Okay, so what's the point of minimax theorem? This course is not a game theory course. Game theory is cool, but we're here to solve some interactive learning problems. Eventually, we care about computation. So we would like later in this course, we would like to formulate many problems as a form of zero-sum game or min-max game. And the solution we would like to derive happen to correspond to some equilibrium of these games. So I want to now define what it means to be equilibrium. We saw a glimpse of that definition at the end of last lecture. I will give you an approximation version, mostly because we'll have algorithms that only theoretically get to approximate equilibrium. So approximate okay, so this is a definition. So we're going to call a pair strategy. This is a game, so we talk about a pair of strategies in a game played by two players with action space x and y. This pair is in alpha approximate sometimes this is called Nash equilibrium or minimax equilibrium for this kind of games. If there are different ways to state this, I'm going to state the one that's closest to the typical way to state what a Nash equilibrium looks like. So the conditions are two inequalities. If the payoff and alpha. Okay. So in case it wasn't clear, like I will continue to use this to be, this is the max player, this is the min player. Okay. Okay, so how do we read this? So I'm going to use x hat and y hat to denote a particular pair strategy. Nothing specific about putting a hat on top of some notation. This is to single out these x hat, y hat to look different from a generic y. Okay. So what are these inequalities? So u of x hat, y hat is how much money the player x is getting, the maximization player is getting. So if you're the minimization player, if you are playing some y, currently you're playing y hat. So an equilibrium is sort of a pair strategy that the two of you simultaneously decided. And equilibrium is also about second thoughts. We all have second thoughts, But in this case, equilibrium is sort of stress testing whether you should or you need to have second thoughts. The second thoughts experiments is exactly asking, well, I'm trying to minimize the money I pay. Knowing that the maximization player is playing x hat, can I do any better by switching? So you and I engage in the game by playing x hat, y hat. Now you look at it and say, well, maybe I could do a little better by switching to some other strategy. In particular, one strategy you could switch to is the best response. This is sort of the best response. Looking at your strategy X hat and try to minimize the money I pay. Suppose I'm the player Y. Okay. So this inequality is basically saying that you might gain something by having the second thoughts and exercise some sort of deviation. So this is sort of a deviation from Y hat. The point is that the deviation won't gain you much. Nothing more than some quantity alpha. Is it clear? Does it make sense? The same thing goes on here. Like now you play the other role where you're the X player. You're trying to maximize, and you look at the pair strategy X hat Y hat, and you start the same second thought experiments. Well, can I switch to a different strategy to get more money? And in particular, maybe you can think about the best response strategy. Knowing that you will play at Y hat, I will take the best response against you to get the most money I have. But this inequality basically said, well, you won't get much beyond what you already had. You won't get more than alpha. Okay. So this is the usual game theoretic interpretation of these sort of results. Why is equilibrium interesting and important? Well, if you're not at equilibrium, like say you and I agree to play a pair strategy, X hat, Y hat, it's not equilibrium, then you would start thinking, oh, I'm going to switch to something else. And then I would do the same thing. So it will not be a stable state. But if we're at the equilibrium, the exact equilibrium, I know I cannot do any better by switching. So both of us might as well stay put. An approximate equilibrium is sort of the approximation of this idea. Well, I'm lazy. Like even if I switch, I won't get more than alpha. I might as well stay put as well. Okay. Any question about the definition? So, maybe it's obvious to some of you, like know that both of these quantities are bigger than 0. Okay, so, because this is like only doing better by doing the best response against the opponent. Okay. All right, so let's get to the meat of this course. This lecture. How do I compute an approximate equilibrium? Last lecture, we basically proved the minimax theorem using no-regret algorithms. It's sort of hinted inside to prove that you can actually compute equilibrium using a no-regret algorithm. That's sort of part of the argument. So we won't redo the same proof again, but instead, here's a sort of a constructive result, a constructive theorem, that basically tell you how to directly get an approximate equilibrium like this. Okay? So here's the result. So suppose I let the two player play this game for a while. So and they generate two sequences of plays. Okay. So suppose I let them play this game. I haven't specified how they will play this game yet, but somehow after they play, they will generate a sequence of strategies. Okay. So they play for T rounds. I'll tell you how they might play this game, but they might play randomly. They might try to use some sort of algorithms like follow the regularized leader, or one player will try to cheat and wait for the other player to commit to a strategy first and best response. Anyway, and we'll look at the average play. Okay, so in particular, So to look ahead, this x bar, y bar will be the x hat, y hat that appear in this definition. Okay. So we'll talk about regrets, and these two players playing against each other, if you isolate each player's problem, they're kind of solving a regret minimization problem, like online learning problem. It kind of is because, right, like if I'm player X, I don't exactly know how player Y will play their strategy. It could be kind of adversarial. The other players generate a bunch of loss functions for me over time. It makes sense to talk about the idea of regret. Okay, so we'll define the regret for one player. Should be a sum there. Okay. As expected, there's a regret for the other player Y, which just switched the order because this person is trying to minimize. Okay. Nothing super interesting so far. I'm just writing down the regret definition. But one player is trying to maximize stuff, the other trying to minimize the same quantity. So the regret just need to do some switching of sign. Okay, so there's a theorem. I believe it was first attributed to Forn and Shapiri. Maybe 96, I think. Yes?
Should there be a YT inside that then, or should it just be Y?
Oh, yeah, okay, thank you. Thanks, Ryan. Yeah, good catch. Good. There's a generalization. I think I'm stating the more general result, which is probably attributed to Gordon, Greenwald, I forgot when. Do you remember when? Jeff Gordon at CMU. And apparently his student doesn't remember when this paper came out. It's all good. Yep. Cool. So the theorem is very simple. It just says, if you look at the average play, this is an approximate equilibrium where the approximation factor is given by the regret with divided by t. Okay. Yeah. Any question about this result? So this is like somewhat general, but one way to interpret this result is if I have some sort of no regret algorithms that both players are running using the gain payoff as the loss function or the negative payoff for the minimization player. This should approach 0. So we'll expand on this later, but we know of algorithms that can generate these sequences of strategies so that both the regret terms are only growing at the rate of square root t. So this quantity will look like 1 over square root t. So you should come to believe that this can be used as a tool for computing approximate equilibrium, where the approximation should go down to 0 at the rate of 1 over root t. And we'll give you some example of how to do it exactly. But let's first see the proof. The proof is 2-line. It's just literally just stating down, putting the notation down. Okay. All right. So what exactly is this regret? Sum of regret over t. Let's write it out. Okay. So this is just like the sum of the two average regret for the two players. So I can write it for the max player first. Okay, that's just a regret for the X player. What should you do when you see this like algebra? There's a lot of stuff going on. X, t, y, t. What would you do from now on? Yeah, this is like screaming, please get me out of here. Like, Okay, so let's cancel them. Okay. There are two ways to prove this, but here's a proof that's more matching with the definition we'll put down. So now we cancel out these things. We can put in like new things here, right? So instead, so I'm gonna. Sorry, I am not on an iPad, so I cannot copy and paste, but let me write it quickly. I'm going to put this utility in the place of these cancellation. Okay, this is again the fundamental principle in mathematics called add and subtract. Yeah, so it's equality. Okay, what should we do now? This has bars in it, like x bar, y bar. These are average plays. The gut feeling is that I want to match these expressions as close as possible. This one also has a white bar here. If you look harder, because this is average. This is like fixing one of the strategy x, taking average over yt, and I guess I'm proving this for the bilinear games. The inequality will go the right way. Let's see. Let's see. I wrote in the notes. So it's convex in y. If I take average, average is higher. Okay, so see. So this one by Jensen inequality. So the assumption I used here is, there's really two steps here, I guess. But the first step is really the Jensen inequality, where I'm trying to fix the maximizer x, and then this becomes an average over t terms where yt is changing. I'm pushing the 1 over t inside. If it's linear, this will be equality, so it will be clean. But this is a convex function in y, so I can apply Jensen inequality, and I believe this is the right sign of inequality. That for the same maximizer, you get bigger than this y bar. Yeah. And similarly, you can do the same thing here because this is negative of u. This u is like concave in x in this more general form of minimax theorem, but it's negative u. So the negative u is actually convex in x. So you can actually do the same switching to x bar. Okay. So I think this basically proved the result by noticing that this is only bigger than 0. This is also non-negative. So we have two non-negative terms that sum up to be something less than this average regret. So each of them, both of them has to be less than the sum because they are like non-negative. Should I do it again? Let me be a little pedantic. This implies So that was the last step I hinted at, so in case it wasn't clear. So this is exactly the equilibrium condition because these quantities are essentially the gain you could have for any single player to deviate from X bar, Y bar. Like, if I'm the X player and I look at my strategy against Y bar, like, can I do any better by switching to a different strategy, in particular switching to max of X? I cannot because this is the inequality that you get out of this derivation. And similarly for the Y player, like by switching to a different strategy, you cannot do better than the average regret. Any question? Okay, so anyway, this is the proof. The key is like this theorem. This theorem gives you a lot of weapons to use. So the result is somewhat agnostic to how do you generate these sequences. There are many choices, and we'll explore these different algorithms. So this could give you different sort of algorithms. I will give you some example, right? So one idea is usually some of us would like to call it the no regret against no regret algorithm. So the idea is very simple. I will put down the notation later, but it's no more complex than just have both players running something like follow the regularized leader. So max player, for example, update xt to be arg Okay, so this R is just some regularization term that you can choose, for example, entropy term. And similarly, you can just do Okay, so these are, just remind you, these are just like FTRL. Both of these are just FTRL. The only thing that looks a little different from what you've seen is how the loss function is defined. The loss function is basically defined by the game payoff, right? So like whatever the other player plays, they return through the game some sort of loss function or payoff function. So you get a loss function that's negative the payoff. So it's the exact same form of algorithm you have seen. Okay, so in this case, you will get right? So like you get these regret term to be the same of at the order of square root t. Right. So you have seen algorithms where these regrets are only growing at the rate of square root t, and therefore if you run it for t rounds, the average play from these no regret against no regret dynamics will give you a 1 over root t approximate equilibrium. Any question? Okay, here's another algorithm that is really perhaps more common, well, in some situation. It's no regret against best response. Okay, so again, X will play follow the regularized leader, same as above. I'm not going to go into the same details. But YT get to cheat. Okay, so YT here, every round I get to wait, actually get to play second. Okay, get to wait, like, oh wait, like now I've seen what X player played, which is like XT. Okay. This is like cheating out with them, but everything is sort of simulation. So inside the algorithms, there might be some hypothetical unfairness, but anyway, this is sort of asking a player X to do the hard work, but letting the other player, the minimization Y, to cheat a little bit to do the easy one, like which is like just look at what the X player play at every round, which is XT. This is coming out of all the regularized leader. Best response. Okay. So here you, of course, will still have the same regret for the X player. What will be the regret for the Y player? 0? Why?
I mean, he's cheating.
Yeah, it's cheating. Yeah, it's no regret. Yeah. So this is if this turned into a philosophy course, this is the darkest philosophy course. Like if you cheat, you get no regret. Yeah. Yeah, so you actually get the same rate. I mean, in terms of asymptotic order, it doesn't matter too much. Both of them will give you something like 1 over root t, but like this is also a entirely feasible, valid way to solve for approximate equilibrium. Any question about this? This is just like instantiations of the theorem to compute approximate equilibrium. And there are really different combinations of how to use this result. Like you can use different choice of the no regret algorithms. You can have these no regret algorithms play against some sort of best response, and so on. Okay. Still have some time. Let me give you one example of how this works. So one of the problem that Drew described in a few lectures ago is called the maximum entropy problem. Okay, so what is the problem? Again, right, so you want to maximize over some probability distributions, P. Everything is non-negative. You want to maximize what is called the entropy. Okay. Again, this is the entropy. All right. So usually the maximum entropy problem is maximizing some entropy function. So you want to find the probability to maximize this function entropy, subject to some constraint. The two constraints, one is, well, it has to be a probability distribution, so this has to sum to 1, exactly 1. Another one is, well, you might have some evidence given by some measurement that the average of some function under this distribution is like some constant c. Okay, so one example I recall in the lecture was you try to roll a die, and the die may not be uniform distribution. It always, over time, after a couple of flips, the average turned out to be 4.5. Right? So you want to find an explanation of what the underlying distribution is for generating such observations. One principal way to do this is to find maximum entropy distribution that satisfy this moment constraint. The moment constraint is the average under this distribution matches with your observation. So this was for the example Drew gave. This is like 4.5. Okay. So anyways, this will come out to, if you solve this exactly, there will be like some optimal value out. Okay, and this doesn't care about how you solve it. Maybe you somehow magically find it. But one way to solve it, as hinted by the previous lecture, is write down what's called the Lagrangian. So the Lagrangian usually take on this form. You want to introduce some dual variables. Okay, just enough space. Okay, so what Drew wrote down a few lectures ago looks like this. If you derive what is known as the Lagrangian, this is called the Lagrange, which is basically introducing what's known as the dual variables, the gamma and lambda. And for everything, for the constraints and the objective you care about, the entropy, into one single function. Okay? And this defines a game. The Lagrangian defines a game. This is sort of the so the game is played between a player who get to choose the probability distributions over some set of outcomes, and the dual player, so to speak. But the intuition of the dual player is, well, I'm going to look at what strategy you play, like what distribution P you choose. I want to identify whether you actually satisfy the constraint. If not, I'm going to set these variables accordingly to penalize through this Lagrangian objective. Right? So for example, if the probability don't sum to 1, I'm going to make this number gamma too big, to be a big number, so that this whole Lagrangian objective will go down. Okay? So it's a little dark, but whenever you don't satisfy, you don't comply, the dual player can screw you up. Okay. Right. But if you take machine learning, you've seen this before. But one of the algorithms for solving this will be, run no regret on the dual player. In this case, this is the online gradient descent. typically, this is the online gradient descent method. And for P, you just want best response. Right? So how people solve this problem is actually simulating the kind of repeated game plays we just talked about. Right? So a lot of time, what people do is you look at this ordering and you run some sort of gradient descent for this set of dual variables. Every time you have updated the dual variable to some values, you will find the best response, the max entropy solutions against these dual variables. And typically it'll look like, you remember a few lectures, this usually looked like this. Where the gamma actually doesn't matter. The normalization constraint turns out to not matter. So how you solve this happen to correspond to some sort of repeated gameplay. And eventually you will converge to some sort of equilibrium. Let's say this is the exact equilibrium. I know the theory doesn't actually get to 0, it go down to 0 at a rate of 1/t, but this is a thought exercise. Suppose I actually get to an equilibrium by running this long enough. What can you argue? Well, so there are a couple of nice things you can say about it. One thing you can say about this is that by applying the equilibrium condition, bless you, this actually matches the objective value, the optimal objective value of the constraint program. So if you write down this Lagrangian game, the game value turns out to be the optimal objective values for the original problem. And one way to look at this is I play some distribution P bar, that's equilibrium, so well that these dual strategies, this dual player, their strategy, cannot screw me up. Okay, so what would that imply? Like no matter how you set these like lambda or gamma values, I can guarantee I reach the optimal objective. What should that imply?
Satisfying the constraints.
Right, you satisfy the constraints, and the reason is the following, right? So like, if I am so confident that I'm playing the P bar so that no matter what you play in lambda and gamma, I can always maintain this value, that must mean that both of these has to be 0. So both of these has to be equal to 0. I will be saturating or exactly satisfying this constraint. If not, I will not be at equilibrium because any gap I leave on the table, you quickly identify there's an arbitrage to really lower the value of the Lagrangian. That would not help me reach the optimal value. Okay, so all of these reasoning is somehow, it used to be stated, well, at least for me, like, a lot of, if you take machine learning optimization, there's this thing called the KKT condition. Have you heard of it? It's all about things like this, like, a lot of things we memorize, and probably happen in your midterm or something. I was really bad at those, but I like thinking about game theory. So like, when thinking about game theory, I could also have a different approach to derive these sort of conditions. Okay. Anyway, any questions so far?
In the best response, the regret can be even negative for y, right?
It could be, oh yeah, that's true. That's great. Excellent. So the point was the regret for best response is like can potentially be negative because you can only do better than the best fix in hindsight. But because you're playing a different strategy every round, you can potentially do better than a fixed strategy. Okay, so let's see. I don't have much time left. I want to just spend the last few minutes talking about something that could be of interest to some of you, and partially because some of the development in AI poker is happening at CMU. Yes.
That argmin, like YT equals argmin, not argmax.
Here? Above.
Yeah. Both argmin.
Both argmin. Yeah, makes sense. Thank you. Okay, so here's a simplified poker game. I don't actually gamble. So I don't actually know how poker works, but here's a simplified game thanks to Christian Kroer. It's an example he gave, and I like it. So well, I want to talk about a type of games called extensive form games. Right? So it looks a little different from the kind of games we've been talking about. Like, you know, the game we talk about always look like we both choose some strategy, and that's it. That's like one shot, almost, there's one shot interaction. Here, sequential form games looks like chess or poker. Like I make a move, you make a move, and alternate, and so on. Right? So one toy example of this is this toy poker game where I believe you play like this. You know, the dealer deal one card. This is not revealed, but only revealed to player one. So let's say you're the player one, and you get to see whether you're ace or king. I believe you win if you're ace. Okay, so the player one will get to see the card and decide to fold or raise. Okay, so there are two strategies. So this is a game tree that model what goes on as the player make the moves based on their information, and based on what the player do, player two can adapt and choose some other strategies like fold or raise. And last round, and then if one of the player fold, the game stops. Okay, so at the last round, the player choose to, I think, seize call or fold. Okay, so and at the end, this is the end of interaction. Like if you fold, it obviously ends the game. But if you call, the player one will reveal the card and only wins some dollar amount if this is ace. So this is the precise details don't really matter. This is not the most interesting poker game, but like there's some ingredients of poker that's pretty interesting. There's some ingredients of the extensive form games is interesting. So usually you go through a few lectures to have formal treatment of everything. But this is an example of extensive form games with incomplete information, in the sense that it's different from chess, right? So like in chess, you look at a board, you know everything. And if you have perfect recall, you know the history perfectly well. Here, from the player two's point of view, player two don't get to see the card dealt for player one. So this is sometimes modeled as an information set. In the sense that from player two's point of view, these two nodes are identical. Like all you know is that the player one raised, and that's all the information you get. And these two nodes are identical. This is a game tree that model the ground truth state of the game, but like, this is only God's view of what's going on in the game. for a player, these two nodes are merged as a set. Okay. Okay, so there are a lot going on with how to solve this sort of game. Like solving poker was regarded one of the most interesting AI challenges for the past 2 decades. And some of the development happened in CMU. So I will basically highlight some of the ideas. One is, this looks arguably very different from the kind of game we've been talking about. Like some player play X, some player play Y, and that's the end of the game. So this is alternating in some order. You can make the tree extremely big. It looks very different. It turns out there are 2 ways to represent these strategies. One is called sequence form. Okay, so there are 2 ways to represent how the players are playing this game. Sequence form is the way to think about this without notation is I want to model how one player would traverse this tree as a funny experiment. Like, I have a cup of water, I have 1 unit of water. As a player, I can pour this water from the root node. The water will gradually flow down to different leaves. And what the player gets to control, at least for the nodes, the blue ones for the player 1, will be controlling how much water will flow through after each node. Okay? Water only goes down, and eventually it will stop at some leaf. And this sequence form strategy, or as a representation, is just modeling how you control the water, how much water flow down to each leaf. Okay? It takes some notation to describe this, but that's really what's going on. And what's cool about this is once you take this sequence form strategy view, this game becomes bilinear. Okay? So it becomes the same kind of game as the kind of game that you can prove minimax theorem for. So it's kind of cool. Like everything is actually linear when you fix the other player's strategy. Okay? And there's another one that's perhaps more natural. It's called behavior strategy. These names sound a little arbitrary, but let me explain. This is more natural in the sense that, this is like choose a distribution over action at each decision point. So, instead of thinking about this water flowing experiment, this is somewhat a local view of what you do in a game. So suppose you reach this node as a player 1, what do you think about? Well, you think about what you do right now. Like what sort of distribution over strategies do you play right here? Somehow this is called behavior strategies, maybe model human behavior more closely. But the variables you keep track of is sort of what is the probability over each actions you play, at each node at the turn of you making decision, okay? So what's the takeaway of this? The fact that this can be written as a bilinear game means minimax theorem holds. And also means that if I get to play no regret, if I somehow implement some sort of no regret strategy, I can compute some equilibrium, approximate equilibrium. So that will be a very interesting way to solve the game. However, I'm not limited to taking this sequence form strategies when I solve the game. I just need some regret minimization strategy. I just need some no regret algorithm. It turns out the more popular algorithm for minimizing regret in this kind of game use sort of behavior strategies. This is sometimes the kind of algorithm usually is called counterfactual regret minimization. CFR. So what it does, I have 1 minute. What it does is the following. Okay, so think about the game from the point of behavior strategy, which is really a local viewpoint of how to solve the game. So suppose you're player 1, you're here. What do? Well, you think. Well, so like you basically think about this tree, right? You're at a tall place. This is a reverse tree. You're standing here, you look down. It's a very deep tree. You're very scared. Okay, well, you take a deep breath and you think about, okay, suppose someone promised me the optimal way to play each sub-game defined by each branch of the tree from now on. What should I do? That is a simple problem. So suppose someone promised me the optimal way to solve each sub-game from now on. This becomes a simple regret minimization problem, at least locally, because here I only get to choose some distribution over 2 strategies, and over time I just need to we weight the probability for these 2 strategies based on the payoff. Okay, that's believable. If someone has an oracle to tell you exactly the optimal strategy from now on, that's what you do. But instead, you don't have that. You have something that's nearly like that, right? So if I promise you for every branch of the sub-game from now on, I don't exactly have the optimal strategy to play those sub-games, but I have the next best thing, which is the no regret strategy over time. Then this idea of minimize regret over the entire tree still works. So this turns out to be a way of implementing a regret minimization strategy over a tree form. It's just initiate a no regret algorithm every single node. So one idea will be literally you'll be playing some sort of follow the regularized leader at every node, and pretend the payoff you get from the subtrees are the right utility to get back. And you just reweigh the probability of strategies based on these historical payoff you get by repeatedly engage with the other player. Okay. So the takeaway is that a lot of the ways to solve poker is literally instantiating like a billion or trillions of no regret algorithms at different decision point of the tree. But they do further engineering to not actually do that over that many nodes. Okay. Let me stop here because I'm out of time. Can take questions later.